All right, everybody, we're going to hope that this works this time. What I'm going to go over for the first video for Chapter 7 involves electron configurations. We're going to take a look at each of the rules that leads to why we follow the order of the configurations that we do, how we fill up our orbitals, and how we place electrons within orbitals of equal energy. So the first rule is off vowels, and that is a word that just means fill from the bottom up. And so with chemistry and electrons, we do that by putting electrons in the orbitals of the lowest energy first. Typically, as an atom, you will find all the electrons for that atom in its ground state, which is the lowest possible energy state in which those electrons can be placed. It's the most stable. If you heat an electron by heating a metal up or heating atoms up in general, you can excite the electrons and force them to move to a higher orbital of energy, and eventually they will fall back down when it's all said and done, and that is called an excited state. You do that with a flame test, which you're going to get to do today. The other two rules are Hund's rule. We talked about that a little bit last class, the caring is sharing rule. How if you have like your 3p orbitals or your 5d orbitals or your 7f orbitals, how you place an electron in one of those orbitals first before you put a second electron in any of the orbitals. And finally, in Pauli's exclusion principle, you cannot have the same set of quantum numbers for any given electron. So the spin, the electrons that are placed in the same orbital, will be opposite so that each electron will have a unique set of quantum numbers. This is the order in which we place our electrons into the orbitals. You start with the arrow in the top left corner and work your way to the bottom right. You do not necessarily have to memorize this set pattern. I'm going to show you a way to get this with the periodic table. But I would like you to note over here at 3D how after we go and fill up 4s, we go back and pick up 3D. Each energy level will start with a row on the periodic table. But when we get to our transition metals, the energy requirement for them will be less if they go into 3D than if they go straight into 4p. And so that's why we see the transition metals falling backwards into the D orbitals and the lanthanide-actinide series falling into the F orbitals. So if you take a look at this periodic table, and this came from your textbook, it kind of talks about the blocks of elements. We talked about this a little bit last week, or last class, excuse me. The alkali and alkaline earth metals will fill their last electrons in the S sublevel, so they are called S block elements. Groups 13 through 18, aluminum, boron, carbon, nitrogen, the halogens, and the noble gases, the exception of helium, will place their electrons into p orbitals. Remember that we start with every energy level getting an S. The second energy level gets a p, so we see 2p here. We move down now to the middle section where we see 3D starting up, and those are our transition elements. And then finally with the F's we get to 4, and that's going to be lanthanides and actinides. And if we continue to identify new elements, we would just keep going on with this process. So there's three ways in which we can write electron configurations. We can write them in the ground state, we can write them in an abbreviated form known as a noble gas, and we can write them with orbital diagrams. Your textbook refers to the ground state as SPDF, and the orbital diagram is orbital box notation. The ground state and noble gases don't specify exactly where the electrons land within orbitals of equal energy, whereas in the orbital diagram you can physically see the electrons, so that's why we have the different ones. A couple more terms before we do some examples. Valence electrons are the electrons that are found in the outermost energy level. They are the electrons found in the highest S energy level that you're in, and if you have like a 4s and a 4p and that is your highest energy level, then those would combine together to give you your valence electrons. These are the electrons that allow us to make compounds. So something like aluminum, which ends in an S2p1, would have 3 valence electrons. And down here is an example, sodium ends in an S1 configuration, so it has 1 valence electron. Whereas chlorine ends in an S2p5, so if you count around the last ring you will see that there are 7 valence electrons. The electrons that are not in that outermost shell are called core electrons. Those are electrons being held tightly to the nucleus by its effective nuclear charge, We'll talk about that in our third video. And those electrons do not have any involvement in forming bonds. So we're going to take a look at 3 of these, and we're going to see each of the ways you can write electron configurations. We're also going to determine if there are unpaired electrons, because that has to do with their magnetism, and we're going to look at their valence electrons to know which electrons are available to form bonds. So boron on your periodic table has 5 electrons because it has an atomic number of 5. And so if I'm going to start placing electrons in its orbital diagram, I will start by filling the lowest available orbital first, lowest energy orbital first, which would be 1s, and I can put a total of 2 electrons there. I would move on next to 2s, which would also be able to take 2 electrons, and after that I'm going to move to a different type of sublevel or subshell. I'm going to move on to 2p, which will take the remaining electron. So to summarize that configuration, I would write 1s2, 2s2, 2p1, with all of the exponents adding up to be the total number of valence electrons, or excuse me, the total number of electrons in boron. The 1s sublevel, or the first energy level, has been filled because I have filled up all the electrons that can be placed there in the s or p orbitals. So I can replace that with the noble gas that has that configuration, helium, and then only show the part that is the open energy level, the one that is still in the process of being filled. And that is known as the noble gas configuration. So helium represents the 2 electrons in 1s, and then we get into 2s2, 2p1. Obviously for boron, for like the period 2 elements, these noble gas configurations aren't the most handy, but especially when you get into the transition metals or the elements in periods 3 or higher, they can be quite beneficial. There is 1 electron in our 2p subshell that does not have a pair, so there is 1 unpaired electron. And because of that, as well as the 2s electrons, those are the ones in our outermost shell, we have 3 valence electrons. Nitrogen is element 7 on the periodic table, so it has 7 electrons. 2 go into 1s, 2 go into 2s, and now I have 3 left. And remember what we talked about with Hund's rule, how we can't place the 2 and the 1 separately, leaving an open orbital. We're going to fill up each orbital with 1 electron first before we start adding additional ones. But that's all the electrons we have, so we're done at that point. Our summary configuration will be 1s2, 2s2, 2p3. Again, your book's going to refer to that as the SPDF. And then the valence electron configuration, helium would take the place of 1s again, leaving 2s2, 2p3. For our unpaired electrons, we're going to look at the 3 that are by themselves. And for our valence electrons, we're going to look at all the electrons that are in 2s as well as 2p, which would be 5. Finally, we're going to take a look at magnesium. Magnesium has 12 electrons. It's element 12 on your periodic table. So 2 electrons go into 1s, 2 go into 2s, 6 go into 2p. And that's taking care of 10 of them. So now we're going to move to a new energy level. We're going to move to 3, and we start with 3s, and we will place both of our electrons in 3s. So our summary configuration will be 1s2, 2s2, 2p6, 3s2. This time we want the noble gas that's in the second row of the periodic table, since all the s and p electrons are filled, and that will be neon, and we will be left with 3s2. Just a little bit shorter to write than the full SPDF configuration. This time there are no electrons that are not paired with another, so we have no unpaired electrons. And valence electron wise, we're just going to be looking at this third energy level, which will have 2 valence electrons. That is the end of this video. Our next video will look at how electron configurations relate to quantum numbers and a few other things.